Okay, good day to all. Welcome to another guest lecture in our theoretical particle physics course. Today, we're honored to have Dr. Cari Cesarotti with us, who will present a talk titled Beyond the Standard Model. Dr. Cesarotti completed her PhD at Harvard University under the guidance of Professor Matthew Rees and then joined MIT as a postdoctoral research associate. Her specialization lies in theoretical high-energy particle physics, where she focuses on developing models, innovating new tools, and advancing data analysis techniques, all grounded in phenomenology. She also contributed to a future muon collider. We hope to see it in our lifetime. During the
Me
seminar, if
too.
you have any questions, please use the raise hand feature on Zoom. I will give you speaking permission. We highly encourage your active participation. Now I'm pleased to hand over the session to Dr. Cari Cesarotti. Thank you for joining us today.
Yeah, so thanks so much for having me. When I first was asked to lecture on this topic, the first thing that came to mind was, of course, that this is an enormous area of very active research. So today I can't even begin to hope to cover every single corner of BSM physics, but my goal for this lecture is to give you sort of an overview about not only what gives us indications that there's BSM physics, but also how you can start to do research in this direction and what are the active ways in which people are researching today. So as was said, if you have any questions or if you want to make a comment or you want to hear more about a certain topic that I introduce, please feel free to jump in with questions. I'd love it if this ended up being more of a discussion too. And yeah, please have no fear. Stop me, interrupt me, ask me anything as we go on. So I think before anyone gives a lecture about what BSM physics is, there has to be some kind of inherent disclaimer. So I can't give you a picture of what is correct BSM physics, given the sense that it is beyond the standard model and we have yet to discover it. So every single BSM theory talk is going to be with a lot of bias in the sense of what problems, maybe one corner of the field finds interesting versus the other. So you can't take this as a complete summary or, the projection of what might actually come out of physics in the future. But again, it's supposed to be sort of a holistic summary of where the field is. So in that same vein, the standard model is really an effective field theory, and we suspect that it is not effective all the way to the Planck scale, but in theory, you could just continue what we have in the standard model up to the Planck scale, and there's nothing deeply pathological about that. That would be a very boring universe, but not something that's inherently inconsistent. So instead, what we're thinking about with BSM research is sort of what kind of things could exist in this intermediate regime between what we can see in our own life and up to this sort of Planckian scale at the 10 to the 16 TeV. So as we go through this again, this is not only a lecture on what BSM physics includes, but also how we can do this research in a responsible, motivated way, given the fact that we don't know for certain what's going on up there and we won't be able to reach a lot of these scales. How can we still research responsibly? All right, so the things that I'm planning on covering in this talk is first, what evidence do we have for beyond the standard model physics? Then we'll go into how you can search for it. And then we'll sort of end with what are some common theories that people use to look and quantify BSM in modern research. So let's get started. There's a lot of things that are still out there today that suggest there could be new fundamental physics. So here is kind of a weird timeline of the different things that we're thinking about. And I kind of want to span it between things that are more theoretically motivated, so things that we don't necessarily see show up in experiment, but are rather inconsistencies in how we formulate the natural world, and things that are empirically motivated. So things that we wouldn't expect to get out of our theory, but show up in experiment, and therefore we must include as an explanation of what the natural world is. So I want to go into detail of a couple of these, and we'll revisit them a lot throughout the talk. And I know that you have a lot of lectures, so there will certainly be some overlap with the content that you've already heard, but hopefully this gives you at least an idea about how you can frame things that you're learning in this class with sort of, the global structure of what the BSM program of modern research looks like. So I think the first most obvious hint of beyond the standard model physics that we have to think about is dark matter. So this is something that we've been seeing a lot in different experiments. And if we think about the matter content of the universe, we've been able to do different measurements that tell us that roughly 70 some percent of it is this thing called dark energy. And then we have the rest of it shared by visible standard model particles and by something that is invisible but still gravitates, which we call dark matter. So this picture already presents a lot of interesting questions. Why should we expect to see something that's invisible? Why should the amount of dark matter be of the same order as the amount of visible matter in the universe? And really, what is the particle content of this dark matter? So we've seen this thing show up in a bunch of different measurements, which gives us a lot of confidence that this is in fact a real phenomenon, not just a misunderstanding. One of the biggest examples that I'm sure you've heard about or you'll see a million times in your physics career is the bullet cluster. So what we're seeing here is that the visible gas that you can see interacts quite a bit when there are two galaxies passing through each other. And so there's a lot of friction between particles. But we can use different techniques to understand where the gravity contours are of different gravitational pulls. And we find that there's a lot of gravity from a lot of mass that we're not seeing that just passed right past each other. So this suggests that there is in fact some massive particles that are gravitating that have very weak interactions, both with visible things and with each other. All right, and then something else that indicates that there's a lot of invisible matter is something called the galaxy rotation curve. So this is very, comes from classical physics. And again, you'll see this plot a million times in your physics career. But if you have a galaxy with some center, you expect that when you have the visible mass, the way that objects rotate around it will follow a certain distribution. And that is corresponding to this disk shape here, is that as you get further away from the center of mass, you expect the velocity of your objects to fall off, right? But as you have a lot of invisible matter, which we call in the halo, there's a lot more mass, which is increasing the gravitational pull. So instead, what we're seeing is that the velocities of objects orbiting are much higher than expected from just this disk model. So again, that's suggesting that there's more invisible data or invisible matter than what we can see. So really, the empirical motivations for dark matter, I think, is one of the strongest things. And has really made this robust research program that we'll come back and talk about, which is this dark matter. Okay, another thing that I think is the most controversial concept of what new fundamental physics is neutrino masses. So I get yelled at a lot by calling neutrino masses something that's not standard model, but the truth is it doesn't have a four-dimensional operator. So I think that it's fair to say that this is something that's beyond the standard model. So you can have a dimension 5 operator if you include into your standard model Lagrangian, which looks like this. Oh. Okay. So if you have this dimension 5 operator included into your standard model, which you can see is breaking lepton number violation, then you have a consistent theory in the standard model that also accounts for neutrino masses. You have this new Majorana mass term. Okay, but because you have this flavor violation, then you start to expect that you can have other processes that violate flavor number and the other leptons as well. So what's going to happen is you have these neutrino oscillations, which is how we were observing this phenomenon at the beginning, is that there's a mass basis and there's going to be an interaction basis, and these two things are going to be different. All right, so the way that we usually like to quantify these things is with what we call the PNMS matrix. So you can define your neutrino states with this matrix, PNMS. And this is going to relate the interaction states with the mass states. So again, while we have some standard model tools to sort of model how this should work, we don't really have a UV completion as to what should generate this operator in the UV. So I still think that neutrino masses kind of falls into this bucket of new physics. And this plot over here is just showing you, again, the evidence of neutrino oscillations based off of the amount of a certain flavor of neutrino observed at the Super Kamiokande experiment. Okay, another phenomena that we have in the Standard Model that we need to explain is the baryon asymmetry of the universe. So usually how we write the baryon asymmetry is with this parameter eta, which is defined to be the number density of baryons minus the number density of antibaryons divided by the number density of photons. And what we would expect is that if this number is balanced, of course, we would expect that this is equal to 0. And this idea that, of course, the baryons and antibaryons can meet and annihilate and just go into photons. That would give us a very boring universe, but that would give us a well-motivated universe too. But instead, what we see is that this ratio is actually equal to the small number, 6 times 10 to the minus 10, which may seem small, but again, given the fact that there are photons literally everywhere in our universe, is actually quite large. So all of this accounts for the fact that we have large-scale structure and things like that in our universe. We know that we can achieve this with the Sakharov conditions. Sakharov, which include out of equilibrium processes, CP violation, and violation of baryon number, which are things that, again, have some components that are in the Standard Model, but certainly aren't all included. So the reason that we have all of this overabundance is something that we don't understand, and yet, is the reason that we can exist in the universe with some sort of structure. Okay, so that kind of gives you this idea about the things that we just sort of found with experiments that we didn't necessarily need to have as part of our theory to still feel like we have a consistent understanding of the Standard Model. So I want to talk now about anomalies, which is kind of this weird intermediate regime between things that are theoretically motivated and experimentally motivated. So this is kind of a tough year for anomalies, so that may be good or bad depending on what side of the argument you want to fall on. But basically, whenever you're running an experiment at a collider or any sort of thing that takes a lot of data, roughly you expect some sort of anomalous behavior to pop up just statistically, right? Is that if you have enough measurements being done, you expect some sort of deviation from your background model at some sort of sigma. When they get very high sigma, like a 5 sigma fluctuation from your background model, that's when you start to take interest. But before then, it's just sort of something that you expect statistically to be showing up. So I want to give you an example of an anomaly that's unfortunately no longer talked about, we think has been completely resolved. It's just a misunderstanding of the experimental analysis, but one that gives kind of a nice idea about what this anomaly business is anyways. So you may have been hearing about measurements of RK or RK star. This is what we like to call a flavor observable. And flavor is a very generic word, right? That just corresponds to one of the different generations of the particles in the Standard Model. And this is the ratio of the branching ratios of a B meson going into a kaon in either 2 neutrinos, or sorry, 2 muons, or 2 electrons. So in the Standard Model, we would expect that this should be 1, right? Is that we expect that the branching ratio into 2nd generation leptons versus 1st generation leptons should be the same. However, when we were measuring it experimentally, for a while we were seeing that this is actually not the case, as instead we were seeing an anomalously low measurement, which suggests that the branching ratios into muons versus electrons was different, right? So this is kind of interesting from a theoretical perspective, because this could be examples of new, even tree-level processes going in. So to get this sort of anomaly in the Standard Model, the diagram that predicts it to be 1 is we have our B meson going to a strange quark through a loop. In our loop, we have another gauge boson being radiated off. And then we know that the couplings to 2nd and 1st generations with these gauge bosons should be universal. So we expect that, of course, this if this is the primary process happening, of course, these two numbers here should be equal. However, if you have some new physics process, like let's say a leptoquark, and we'll talk more about these later, is now instead you can have a process that looks like this. And so now you have a tree level new physics process that can alter this loop level standard model process. And that could give you this very small deviation. Unfortunately, it turned out to be something in the calibration, I think, of the detector because muons and electrons experimentally look quite different. But we were all very excited for a while that perhaps it could be evidence of this new physics popping up. So anomalies at colliders are something really interesting that we like to pay attention to when looking for new physics. Another anomaly that has been taking the news cycle pretty often is the G-2 experiment. And so that's what this number over here is. So there's the G-2 experiment at Fermilab. Basically what it's measuring is the correction to the coupling that looks like this. So here would be like the first loop diagram, but then of course you can have all kinds of crazy things running in this loop. We used to think that this measurement was in a 5 sigma tension with standard model, but then once you include the most recent lattice results, it becomes only a 1 sigma tension, which is something much more reasonable. So this is kind of the game that we play with anomalies, is that, you know, sometimes they show up in experiments, especially when you have many measurements ongoing, but the actual theoretical motivation may or may not persist. So anomaly searching is something that is going to definitely be a part of your life as a BSM researcher, but it's kind of hard to motivate a whole research program on. All right, so now I want to move into this kind of very differently motivated zone, which is things that just kind of are pathological in theory, but we don't necessarily have an experimental answer for. So I think everyone who's ever thought about doing physics has certainly heard about either the Higgs or Higgs phenomena, or the fact that there's this hierarchy problem. So I want to just talk about that really quickly. So in the standard model, we suspect to have this scalar potential with our Higgs particle that looks like this, where we have this quadratic term and this quartic term, and that ultimately gives us this wine bottle potential, right? So we have this Higgs particle, and we want to understand what its mass should be after this pattern of spontaneous symmetry breaking. So we can measure its bare mass very well by checking what this number should be at the standard model. But we find that this is kind of an unsafe thing. So here's the problem with scalar masses, right? Is if you have the scalar mass term, you expect to start to see corrections when you go to the quantum picture, right? So when you're trying to renormalize the mass. So if you just have these diagrams with single loops, okay, so you have a loop where you have all the Higgs flowing in the loop, and then you have a loop with gauge bosons, and you can have a loop with the various fermions. And it turns out, if you're adding up all of these single loop contributions, you end up with quantum corrections that are quadratically divergent. And so this is a very big problem if you think that the scale of new physics to show up on is equal to the Planck scale. So if this is equal to the Planck, which is 10 to the 17 GeV, given that the mass of the Higgs boson is only about 100 GeV, suddenly you have a fine-tuning problem of 10 to the 32, right? So you are 32 orders of magnitude off from what your theory would predict. So that's something that sits quite poorly with us as theorists, even though experimentally we have been able to verify what the mass of the Higgs should be. So the hierarchy problem and just sort of Higgs phenomena in general are something that really preoccupies a lot of what we think about in theory. Why should we have this new fundamental scalar particle when there are no other fundamental scalars? There's a lot of things that just kind of are unanswered from a very fundamental perspective. Okay, grand unification is another idea that's been very important in shaping how we think about the UV. So if you think about what the couplings are in the standard model, we can do a little sketch in terms of the energy scale. and then 1 over the various couplings. So if you want to think about alpha E and M, again, don't take any of these numbers too seriously. It's just supposed to give you general behavior. Then we have the electroweak, or the weak, I guess. And we also have the strong coupling. Okay, and we find that there's this really frustrating behavior that if you take all these couplings and you run them up into the UV, you find that they almost interact at a single point, but they don't exactly, right? So that tells us that the beta functions of these things as they run are not going to rejoin to a single force. So the idea with grand unification is that, in fact, the forces are all unified in some UV. And so again, if you draw this, you're going to expect that all of these forces recombine at a single point. And I didn't do a great job of drawing those straight, but the idea is that there should be some energy scale, which is the gut scale, which is, maybe sitting around from predictions 10 to the 15 GeV. So clearly that's much higher than what we can probe experimentally. But the idea is that if you have the standard model, which we expect to be this SU3 color cross SU2 left cross U1 hypercharge, is that this can fit in some subgroup of some bigger group that would explain why all of these things should unify. So the most basic idea is that you have sort of this SU5 big group, which is the most minimal thing that can fit all of these different groups inside of it. But you can also get much more exotic in terms of your algebras and think about things like SO10 or even higher representations. But the idea is that, again, you're restoring some symmetry as you're running up into the UV, and that's allowing you to sort of come back and unify your couplings at this one point. So this tells you basically where the symmetry breaking of the higher group would occur, right? So this would be really nice from the perspective that, just looking at this sort of gauge structure of the standard model seems very arbitrary and very ad hoc. So having something like gut that could explain a single symmetry that's then broken for various reasons is something that would really sort of add a more fundamental picture to why the universe is the way it is. Another problem that we think about is strong CP. And this is a problem that, again, kind of goes in with the hierarchy problem in the sense that there's some fine tuning happening. You can think about it classically as the angle between up quarks and down quarks in something like your neutrons. So you would expect kind of naively these things to be like aligned randomly with some finite angle theta. But what we find instead is that theta is very close to 0. Okay, and so what this corresponds to in terms of the quantum picture is that the CP violation in the strong sector is actually quite small. And so it's so unnaturally small that we have no idea why, in fact, it looks that small. And again, having any sort of number that could be any finite value, but instead is extremely close to 0, is something that doesn't sit very well with us in terms of having some greater motivation. So the fact that this number happens to be 0 without some sort of general symmetry forcing it to be 0 rings some alarm bells that maybe there's some underlying symmetry that we're not understanding that would explain why this could be. Okay, then finally, something else that I think is an important question for wondering if there should be physics beyond the standard model is just sort of looking at the arbitrarity of the standard model. And so by that, I mean like this flavor structure that has occurred. So it's really interesting that if we look at our standard model and the particle content, there's these 3 generations in both the quarks and the leptons, and they have this sort of little hierarchy between them of the masses, and they couple differently in terms of thinking about, like the CKM matrix, the masses of the generations, and so on. So, again, we talked about how the gauge structure itself is a little bit arbitrary, but also the fact that we have these 3 generations and there's not really some deep reason to explain why some are more massive, why they couple to the Higgs more strongly, why some have more CP violation than other in processes. This is something that, again, isn't inconsistent, but is something that's not explained by a fundamental theory. So again, if you want really to model the most fundamental aspects of the universe, this is a question that you should probably have an answer to. Okay, so this is again just a couple of ideas that we can consider when we're thinking about the big landscape of BSM physics. Certainly there's many more reasons, but I think these are kind of the broad lampposts in which people formulate a lot of their research opinions. So hopefully that's enough empirical evidence, theoretical motivation to think that BSM physics is something that requires a lot of active attention in terms of modern research. So before I go on, any questions about some of the examples, some of the experiments, any of the results as to why BSM physics is certainly out there? Okay, if not, we'll continue. All right, so given that BSM is certainly something that's in our universe, the question as researchers should then be, how do we actually look for it? So just kind of from a philosophical point of view, it should kind of be surprising to you, or at least seem like it's a difficult challenge to be searching for something that you don't know what it is, right? As a researcher, this should ring some alarm bells about how do we actually identify something new when we're not sure what we're trying to identify. So this could be in kind of a difficult way to motivate how you're researching because, you know, you might have too much of a theory bias, you might not be building the right experiments to look for something, or you might be misled by the kind of questions that you're trying to ask. And these are all very possible routes that you can go down as pitfalls when we're trying to search for BSM physics. So even though we don't know what the answer is going to be or necessarily where to look, there are some sort of ideologies that we can adopt to make sure that we're doing this research in a responsible way. So if you're going to propose a BSM model, the first thing that it should do, because we are all people using the scientific process, is that it should be testable. You can't come up with a theory that says, okay, there exists some new particle that's completely sterile and only appears at the Planck scale and has no interactions with any other particles and give yourself a Nobel Prize, right? Like there has to be some sort of connection to the standard model in a way that we can test it if you're going to come up with a verifiable theory. All right, there should be some motivation. Of course, it's quite tempting to just want to say, okay, any sort of Lagrangian that we can write down, why not do it? Why not see what's out there? But again, if you're just shooting in the dark, every single theory is a measure 0 point, right? So just making up ideas that could be consistent isn't going to be the best way to actually discover something new about the universe. And then my final point is something that I think is actually quite difficult to reconcile with is that it needs to be compatible with existing measurements. And this last point is surprisingly difficult to make sure that you're incorporating in your research because a lot of the times what you are probing can have effects that you're not necessarily expecting to in terms of other measurements that have historically been done on standard model phenomena. Okay. So I am a collider theorist, so a lot of my story is going to be shaped by what we can do at colliders. But I hope the broader point still stands. So we've been able to collect a lot of evidence around here, right? Because the world that we live in is sort of in this sort of intermediate energy. We have protons and neutrons sitting naturally at about a GeV of mass. And chemistry happens at about the KeV scale and things like that. So there's a lot of evidence that we've been able to collect either from just the natural world and its roughly ground state, and then going up to these higher energies in a clean environment by using experiments like colliders. And of course, we can start to probe earlier times and things like that by doing cosmological experiments. And by going back in time, we also go to higher energies. But as we do that, we also sort of get less clearly interpretable data as well. So it's not that anything sort of below the energy that we can't achieve is completely visible to us. Certainly there can be new physics that couples to us that are very, very light or low in this energy scale. But if they're coupling so weakly to us that they're so rare they can evade our observation, there can still be new physics in that scale as well. Okay. And so we leave this cutoff here at this 10 to the 16 TeV, which is the Planck scale, because beyond it, we can start to form black holes. But of course, new phenomena could also arise beyond that, right? It's just probably not going to be best described in the language of particle physics. So our hope when we're doing BSM is that we can sort of carve out this area here and understand what could be going on and how these effects in the UV can bleed back into the IR in ways that we can observe with our terrestrial experiments. Okay. So the fact that the standard model has done remarkably well means that we have to make sure that any sort of new physics conjecture is consistent with our previous experimental results. So this can be something that's both difficult and sometimes surprisingly unconstrained. And what I mean by that is, there can be ways in which new physics at high energies can generate these effects at low energy scales in very non-canonical ways or ways that you might not think of immediately. But it's surprisingly unconstrained in the sense that many experiments, both terrestrial and cosmological, astronomical, whatever, are highly model dependent. So again, any one theory of new physics is going to be a measure 0 points in this vast parameter space of what new theories could be. So having sort of a specific model is probably unlikely to be the exact scenario of new physics unless it's extremely well motivated. Okay, so let me kind of get into these two different areas and describe how we can make sure that we're doing things that are both unconstrained by new physics and sort of model robust, so we're not just poking around randomly in the dark. All right, we'll start with things that are difficult first. Okay. So I've given this picture kind of a couple times about our energy scale. With the LHC right now, the LHC functions at the center of mass of about, I think, 13.6 TeV is what we're running at right now. But because we are colliding, oh, I see a question actually in the chat. Okay, do you think that cosmological measurements have a bias, or is it a problem that could be solved by introducing new physics? Okay, so this is an interesting question. I think that cosmological measurements aren't necessarily biased, is the way to think about it, but instead cosmological measurements have a lot of uncertainty in the sense that a lot of data from what we look at is kind of obfuscated in a way. If things are happening before Big Bang nucleosynthesis, basically there's no sort of observable that we can have that would still have remnants that we could see today. So a lot of what's difficult about interpreting cosmological data is just that so many different new physics phenomena could explain things that we see. So kind of how I would encourage you to think about looking at the interface between cosmological data and collider physics is that you might see some hint of some kind of new physics in cosmology, and then to uniquely define the new physics model that it corresponds to, you sort of have to do it in this much cleaner environment where you can produce new degrees of freedom on shell or say things that are much more like definitively provable. Because again, the stuff that happens in the early universe at very high energies a long time ago, there's a lot of things that we could see now that would be consistent with it. But yeah, it's an interesting question. Okay. Good. So coming back to this picture of the energy scale, right? The LHC kind of taps out more so at the TeV scale because we're colliding composite particles. So the energy of the individual collisions are going to be much more like 1 or 2 TeV. So anything above this energy scale are things that we don't really have direct windows into so far. Okay, and so what could be happening at this new energy scale could be recognized in the IR. So we'll call this the IR, and we'll call this the UV. And so new physics happening in the UV could be generating effects in the IR by higher dimensional operators is how we would see them. So we can consider having some sort of operator that has roughly this form for D is greater than 4. So if you remember from lectures, you have sort of these different classes of operators. If they have a dimension, less than 4, then we call these relevant operators. If we have something that's equal to 4, then it's marginal. And if we have something greater than 4, then they're irrelevant. So because you would see the coefficients of these higher power operators showing up with the suppression of a high mass scale, the higher in the UV that these new physics exists, right, the smaller of an effect it's going to have in the IR. So one way that you can kind of always sort of push the effects of this new physics out of the realm of sensitivity that you have by making it too weakly coupled to standard model interactions is by pushing your operator, by pushing your new physics higher into the UV, and therefore your operator that it's generating in the IR is less and less strong, right? So this is something that you can always do, but again, it's not super motivated to just push it up arbitrarily high. So basically we want to see evidence, goodness, of these sort of higher order operators at moderately high energies in the UV, and not just things all the way at the Planck scale that couldn't be consistent. So let's talk about first an example that's really nice in the standard model about the evidence of new physics in the UV that wasn't at a crazy high scale, but was instead at roughly the TeV scale. So I don't know the rough age of this group, but I was certainly alive and doing physics at the time of this. But basically, we built the LHC, or the LHC was conceived and then built with the idea that we would have to find the Higgs, because a phenomenon was occurring in our theoretical calculations called the violation of unitarity. Okay, and so what this was that we were calculating a cross-section of just standard model processes, and we were finding that the probability of this happening was growing arbitrarily with energy. So if something grows arbitrarily with energy, as we push to higher and higher energies, we expect just the probability of this to diverge. And clearly that cannot be a statement of our physical universe. So basically, what was happening is that we had this diagram where we were scattering 2 gauge bosons and then looking at, sort of just a straightforward scattering process where you get the same bosons coming out. And if you do this calculation naively, you find that the longitudinal degrees of freedom will give you an amplitude that's growing with energy, right? So this had to be something that was inconsistent with, this had to be something that was inconsistent with the standard model, because clearly this can happen, right? So what was actually happening, right, is that secretly the W was part of the gauge boson of the SU2 left group, but the longitudinal polarization of this was coming from the Higgs. All right, so there was a new degree of freedom that was only visible when you went up beyond that symmetry breaking scale of the Higgs boson. So we call this the Goldstone equivalence theorem, that these low energy degrees of freedom, which correspond to the symmetry breaking, are equivalent to this higher energy theory where you have the restoration of the symmetry. Okay, and so what happens is if you actually include the diagrams with Higgs scattering instead of just the WW scattering, because secretly, again, it's the Higgs interacting as the longitudinal degree of freedom for the W. Once you find that, then you've regulated the diagram, is that this behavior that grows with energy is going to be canceled by a different diagram, and no longer is this going to be divergent energy. So the fact that we had some amplitude that seemed like it was going to diverge told us that at the energy scale of roughly a TeV, there had to be some new degree of freedom showing up. And of course, what we saw was our Higgs, which has a mass of this 125 GeV. So this is perhaps one of the most famous examples of something in the UV generating effects in the IR that indicate at what scale we expect to see new physics showing up. Okay, So we can think about this in sort of a more generic way. The standard model EFT, which is called SMEFT. You can guess where that comes from, standard model EFT. Okay. Is giving us kind of this consistent way to think about if there could be other physics in the UV that's having effects in the IR. So generally, when we think of the standard model, we're thinking about, again, these relevant operators, these less than degree 4 or less than dimension 4 operators, these marginal operators, which are at dimension 4. And then we can start to think about these Lagrangians that consist of these higher dimensional operators that are going to need some sort of discussion of what happens in the UV. So at dimension 5, there's only one operator. At dimension 6, I think there's 60 operators per generation. And so you can imagine that the number of operators gets larger and larger and larger by the number of dimensions we allow there to be in the operator. So usually we think about this as just the renormalizable standard model. All right, that's showing up more and more. This has the single operator that we've already talked about, which is this Weinberg operator that can explain the neutrino masses. And then anything that's showing up for this dimension 6 operator is going to be have its effects suppressed by the energy scale in which you are doing the measurements over the scale of new physics that's generating the operator. Okay, and of course, these things are also going to start to be likely loop suppressed and things like that if it's caused by quantum effects as well. So it might seem like there's kind of infinite operators, but keep in mind that, you can also do things like solve the equations of motions of particles, reduces number of operators. There are symmetries in the standard model that prevents just any random operator from being written down. But generically, yeah, anything that is consistent with the gauge groups of the standard model, consistent with the gauge groups of the standard model and allowed by Lorentz symmetry should be included in these higher order operators that could explain what's going on in the UV. So oftentimes we'll talk about these ideas of Wilson coefficients for these 6-dimensional operators. So maybe you've heard of these. So again, they're characterized by some coupling, which is usually order 1, some scale of new physics, which happens in the UV, and then an operator that has dimension 6. Okay, and so the idea is that, if you have something like a diagram like this, where you have 4 fermions, you can sort of collapse it into a single point interaction. And then with 4 fermions, this will be a dimension 6 operator with some effective coupling over some energy scale. Right. So basically what you're doing when you go from this diagram to this diagram is you're saying, okay, if my propagator looks something like the mass of a new physics squared minus the energy that it's carrying, if the mass is just so much higher than whatever energy, wow, that's really showing up a lot, huh? If the mass is so much higher than any energy that you're actually doing the process at, then this can effectively equal just 1 over the mass, right? And so then that just looks like a single coupling. And so that feeds back into just an effective coupling onto your operator like this. Okay, so of course, all of the couplings that you have in your Wilson operators are going to be a function of this new energy scale. And often when we think about things with like Higgs physics or whatever, we take our energy scale to be that electroweak scale. So this is often the scale in which we're currently measuring things. But of course, as experiments improve, we hope to be able to push that energy scale up to higher and higher energies. All right. So as you do this sort of Wilson coefficient expansion and think about ways that new physics can show up, again, any operator that can appear should appear unless there's something that's explicitly forbidding the symmetry to occur. Okay. So what SMEFT is it's really this integration of all of these operators. And whenever you're making measurements, you should find you should make sure that any sort of measurement that you're making is going to be consistent not only with the low energy renormalizable operators, but also with the effective operators that could be generated by even standard model effects at higher orders or through loop effects or things like that. Okay. So the way that we can utilize this to actually make predictions as to whether or not there are standard model or BSM phenomena showing up is that we can perform these global fits of data using the SMEFT framework, right? So it's kind of hard to sort of optimize over all of these different operators at once and think about how every sort of new physics event can be showing up in all of these different ways. So instead, we're going to think about sort of the global set of numbers that can be measured in the standard model and try to devise a way to make sure that any new measurement of some standard model parameter is consistent with everything that's been measured so far. So these are called global fits. And let me give you an example of a recent anomaly that has popped up. Okay. So if we're thinking again about our Wilson coefficients in this dimension 6 of our Lagrangian, here's just some examples of operators that can show up. So I gave you that very simple 4 fermion operator, but this is just an example of things that could affect a Higgs measurement in these operators. So again, there should be, I think, 62 per generation. And here are just the things that would affect things pertaining to Higgs width, Higgs mass, Higgs coupling, things like that. So yeah, the Higgs is a particularly dangerous particle, as we talked about before as well, because you can always make this gauge singlet by doing H dagger H. So this gauge singlet can couple to any other gauge singlet in the standard model, and that can generate all sorts of interesting new effects that perhaps you wouldn't have expected before. Come on. Oh, there we go. All right, so let's consider a concrete example. Okay. About how we can do these sort of global fits. All right, so again, we talked about all of these different operators in this Wilson operator framework. But it's not like when we are looking at cosmological collider data, we can just pull off different coefficients on certain operators, right? Instead, what we have to do is look at actual experimental observables that we can get from data, because we can't measure bare parameters with Lagrangian with just collider events, right? Is that we have to actually think of some observable that can be affected by these operators. So given this big set of operators we just saw that affect the Higgs measurements, those exist for all the particles of the standard model, and then are influencing these different kinds of observables too. So of course, this is not a complete list of all the observables that we can have in the standard model, but here's a nice list of things that we can measure very well in the standard model, right? And all of these things are going to be functions of not only coefficients on the renormalizable operators in the standard model, but also including effects generated by these, right? So what we're not showing you here is that these are functions of all of these CIs that can show up in your Wilson coefficients as well. So when you make a measurement at a collider, you might expect from your theory that, okay, I'm only seeing things that show up with the operators in my standard model. But the truth is that you might be seeing additional effects that are reweighting how the different coefficients of your operators are contributing to the measured values. So the idea is that first what you want to do is you want to build your set of very well measured things. And then you want to fit your theory, oh my gosh, fit your theory over the measured values. So what's saying here is that basically, you know, just because you have a theory that you suspect describes what's going on and what these observables are secretly functions of, the fact is that there might be other contributions, right? And so it's not necessarily pathological if there's some new physics effect that's, you know, giving you this additional contribution to something like the Higgs or the Z width as shown here. But what you have to make sure is that the effect that would be generated to influence the width of the Z also has to show up in any of these other operators as well. So maybe some effect that would make the Z width wider than you would suspect, but also do something like change the mass of the W. So what you need to make sure is that if there is something that could change the Z width, it also needs to be affecting all of the other relevant operators as well. So that's when you take your theory and you fit over all of these different values at the same time. From that, you can get predictions of the standard model. And then you can actually compare the standard model predictions that you have doing this fit with further experimental variables. So you want to measure some sort of subset of the total observables you can see with the standard model. And then you want to compare that to the experimental result that you would see from other experiments as well. So let me give you a more concrete example, since this is a very broad idea. So something that has cropped up recently is this W mass anomaly that you may have heard about. So basically the W mass has been measured by a bunch of different experiments. It's been measured first at Fermilab, I think, and then with other corresponding experiments like Atlas at the LHC. So recently, there was a reanalysis of the data taken at Fermilab that says that the mass of the W is actually much, much higher than we expect it to be. So this right here, if we just take this number completely seriously and we compare it with what we would expect from the standard model, this is at a 7 sigma tension with what we predicted the standard model to be. All right, so if this number alone were what we took as the measurements of the mass, clearly we've done something wrong in our theory, right? Clearly there are additional contributions to the mass that we have neglected to include that would generate such a high mass experimentally. So let's say that if this is truly the mass of this W that we're measuring, are there kind of new physics effects that could contribute to this? So the way that we do this and the way that we test sort of broadly over what kind of class of new physics models that could contribute to this is by doing this sort of global fit that I just described that we call electroweak precision. So the idea is, again, that we have some observables that are measured very, very well. All right, and so these things have all been measured very well experimentally. Okay, and then what we want to do is we want to write other observables as a function of a subset of them. So we'll say that, okay, all of these things have been measured, all of these things have some experimental value, but we want to take all of these and make any sort of other observable a function of these 5 parameters. Okay, so you're calculating these observables using these other observables. And we can do that again because the standard model only has a fixed number of free parameters, right? So if you make a certain number of measurements, one for each free parameter of the standard model, then in theory, any other observable you can make with the standard model should just be a function of those observables, right? So if you're measuring 5 parameters and you only need 5 degrees of freedom to calculate things, then you can expect that you can actually reconstruct all of these other observables using the very well measured numbers, right? And so then, I'm so sorry, this keeps showing up. I don't know why. Well, I suspect I do know why. My disk is full, I guess. But yeah, basically, if you can measure something very precisely in the standard model, you can then leverage that to make other precise predictions and see if things are consistent or not. So if we just take the standard model as our theory and we take the measured values of these observables here, and then we try to use it to compute the W mass, we find that we're wrong, right? We find that we're wrong with a 7 sigma tension, right? So the idea is, how can we change our theory and modify it to have some sort of new physics or beyond the standard model phenomenon that when we calculate the mass of the W, including this new physics, is that we're getting something that's actually consistent with what's being experimentally measured. Okay, so that's sort of the framework of what we're doing, right? Is that we're not like recalculating all of these single operators. We're not seeing how every single operator could possibly be adjusted by any kind of new physics, but we're taking this global perspective that if we change the theory, which changes how we calculate things as a function of these 5 parameters, is there a theory in which we can get this value that doesn't have this enormous 7 sigma tension? Okay, so I hope that that's a little bit clear. So the theory addition that we add, for example, would be to add what we call these oblique parameters to our theory. So again, we're sticking with these as our 5 well-measured observables. And then these are all written as a function of these 5 observables, but then we're also going to be adding 2 more parameters to our theory. So what we're doing is we're calculating all of our observables as a function. All right, I think I might need to deal with this to get rid of this error, but okay. We're calculating all of our other observables as a function of these 5 numbers up here, and then also these 2 new parameters, these oblique parameters, which are generated by new physics. Okay, so all of our observables down here should be written as a function of the 5 things up here, and then the 2 new parameters here. So in the standard model, we expect S and T to be equal to 0, but with new physics, S and T are non-zero. So exactly what S and T equal and how they affect the functions of all these other observables here, that's going to be a function of, sorry, I'll deal with this right after this section, but all of how S and T exactly are formulated is a function of your new physics model, but just including this S and T parameter has a very robust way in which it affects a lot of these observables down here. So since we're talking about the W mass, let's just talk about how the W mass gets affected. Again, you can see that it's written only as a function of these 5 observables plus S and T. And if ST and this other observable U, which we set to 0, so we won't worry about it. But if S and T were equal to 0, then we would again just recover the standard model prediction for both of these observables, both the width and the mass. So it's including these 2 new parameters as non-zero things that could be able to account for the fact that this number is so much anomalously higher than what we expect with just the standard model. Maybe if I erase things, it'll complain less, but okay. All right, so just to give you sort of an example about how this actually worked out in research, in this paper, what we do, this is very shameless. I'm just gonna talk about my own paper, although of course we are not the only people to ever do this method. But if you take this framework and you try to fit for what S and T should be by using all the well-measured observables that you have, and the experimental results of all your variables, which are a function of the well-measured observables, you find the following results. So what you would expect from just having the previous results of the W mass is that S and T could be perfectly consistent with being 0. That's what this blue curve is right here. It's just from old data without this new measurement that's so anomalous. So before, S and T could be 0, the standard model could be the full story, nothing was a problem. If we go to the most extreme example, which is which is taking just the new result as the full, as the true result of what the W mass should be, we see we get this red contour appear, which doesn't include the 0, 0 point at all, right? So what this is saying is that no, there has to be some new contribution to new physics. Otherwise, it's completely inconsistent with the standard model up to 2 sigma, right? So what this is suggesting is that with this new measurement, some value of S and T is likely sitting in this region rather than in this previous region, as suggested by the standard model. Okay, so then the name of the game is that you want to come up with some sort of new physics model that can consistently give a value of these new parameters that sits in the regime that you would expect from the measurement. All right. So again, just saying that S and T should be non-zero doesn't tell you what the model should be. It just tells you that there should be a model of new physics. All right. And so a model that we introduce is this scalar triplet model. And so the idea is that we're adding some new, we're adding a new particle, which we call phi, which is a triplet under the SU2 of the standard model. So we'll say that phi is a scalar, and it's an SU2 triplet, meaning it has 3 degrees of freedom here. So if we do the standard model plus this particle, the interactions that will generate that are still standard model singlets are these following operators. Okay, so basically you can have a kinetic term, a mass term, and then you have these interactions with the Higgs boson. So you might not suspect that just writing down this theory here, where you have no W's or Z's included at all in your theory, why would you suspect that this would impact so greatly the mass of the W, right? That's kind of a surprising result, that adding some particle that doesn't even talk directly to the W would then change its mass quite dramatically in measurements. Okay, but as we talked about with the unitarity problem, right, is that secretly the longitudinal degree of freedom in the W is from the Higgs boson. So if you are doing things that interact with the Higgs at high energies, that will have an impact on what we see in the low energies of these particles, right? So if you're adding something that's going to mix with the Higgs, then it will also secretly talk to the longitudinal modes of the W as well. Good. So we found that when we include this additional particle, is that a way that we can produce S and T's that are consistent with what the fit of the standard model should be, given this anomalous W mass, is that these parameters in our new model, and this guy, yeah, so given this Lagrangian, if the values of the Lagrangian, the bare couplings, take on a value that's in this blue band, then you generate a new physics contribution to the W mass that is consistent with the global fit in this 2 sigma contour. So this was a very long example, but hopefully that you see the point that you can write down new theories of physics that look like they have nothing to do with other parts of the standard model, but because of higher dimensional operators that they generate, or other ways that like the UV physics can influence the IR physics, there's a lot of non-trivial ways in which all of this stuff mixes together. So this is what I mean by it can be very difficult to make sure that when you're writing down a new theory of physics, is that it's not actually going to get in the way or ruin some previous measurement or prediction of the standard model. Okay, so I think before I go on to this next section, I should deal with my iPad troubles. So maybe now would be a good time. We're about at the halfway mark anyway, so maybe now would be a good time for like a 5-minute break, if that's okay. Okay, can you explain about Bayesian evidence being affected by adding more standard models and how? Okay, yeah, so this is an interesting question about statistics that I don't think I can answer too deeply. But yeah, I mean, so of course, if you just want to if you're doing this fit over all the parameters of the standard model and you just keep introducing more and more and more parameters, right? Like doing an infinite parameter fit is the same as having like a non-renormalizable theory again. And so the problem with that is that we're no longer predictive if you just have like more and more and more parameters, arbitrarily many parameters until you get some sort of perfect fit that's not really theoretically motivated. So when you're kind of choosing like what new physics models are best candidates, certainly the goodness of fit is something that you need to consider, like how many different tensions are you introducing, and like what kind of things are you resolving by changing the fit. But also, we need to kind of function, going back to the idea of doing a responsible BSM, we need to kind of function with the idea of like Occam's razor, right? Like what is the most minimal model that you can conceive of that has some inherent motivation to explain it versus just, like if you were to say, like the standard model is explained if I put in like 2 extra GeV scalars. It's like, okay, but like that's a pathological model. Why on earth should we believe that? Yeah, so doing the global fit by just introducing new parameters, it's not super theoretically well motivated. I wouldn't say is a way to like gain insight on the standard model. Like just because your theory matches observations doesn't mean it's predictive and doesn't mean that it's like a healthy theory, if that makes sense. Okay, these are great questions. Thanks, guys. Okay, so I will jump back into this discussion of the EFT approach of the standard model. So I just gave you a very specific example, which was the WMS. But of course, there are other sort of anomalies or predictions or whatever that we can sort of use this EFT approach to gain insight about what things are consistent or inconsistent with the standard model. Okay. So part of understanding when energy scales of new physics should be arising is also understanding when we have this idea of violation of accidental symmetries. All right, so accidental symmetries are global symmetries of your model that only are appearing because you truncate at a certain order of your operator dimension. So the idea is that oops, sorry, my notes got a little out of order. Yeah, okay, so the idea is that you have dimension 4 and below operators, and the operators of this dimension might respect some global symmetry that isn't a real symmetry, but just shows up accidentally because you're not including these higher dimensional. Yeah.
Do you intend to share your screen?
Oh my God, am I not sharing my screen? That's terrible. Thank you so much. I was just writing on it so happily. Okay. Okay, great. Can we see again?
Yes.
Okay, great. Thank you so much for stopping me. My goodness. Okay. So yeah, the idea is that because you're truncating the operators in the Lagrangian up to this dimension 4 of relevant and marginal operators, is that you can have these additional global symmetries that are broken with higher dimensional operators. So that means that if you have some sort of observable in your model and it predicts that an accidental symmetry is broken, this means that the effect of it has to come from something in the UV. Okay, so there's a lot of nice examples that I can give you that were really standard and to talk about for these beyond the standard model new physics ideas. So one of them is called the custodial symmetry of the Higgs, which is this additional global SU2 symmetry that we find from the Higgs mechanism. So if you remember, the representation of the Higgs is a color singlet and SU2 doublet, and then 1/2 under hypercharge. And the fact that it's a doublet under SU2 means that there's 4 degrees of freedom with the Higgs, right? It's like the Higgs is actually described by 4 particles. Okay. And what happens is after spontaneous symmetry breaking, right, we have only 1 degree of freedom that we specify gets this that we would specify would get this VEV, and then the other 3 have 0 VEVs, right? And we know the story that these other 3 degrees of freedom get eaten by our gauge bosons and they turn into the longitudinal modes of these bosons. But if we were to consider a standard model first that has no, that's big. If we have no U1 symmetry of the standard model and we're just thinking about SU3 cross U2, then what happens is if you take your kinetic term And after spontaneous symmetry breaking, what you would see is that the mass of the SU2 gauge bosons are all equal. Okay, so you wouldn't see this W plus, W minus, Z boson. You would just see that there's one mass, and then you have these 3 degrees of freedom that propagate. Okay, so it turns out that, you know, we do have this extra U1 symmetry of the Standard Model. And because of that, right, that's what tells us that, all right, now we have really the W plus, the W minus, and then the Z and the gamma, which are the neutral degrees of freedom. But the fact that there's this SU2 symmetry within the Higgs degrees of freedom that persists even after this spontaneous symmetry breaking, what this tells us is that there's a well-defined relationship between the mass of these particles, given that the Higgs degrees of freedom are related by a symmetry, right? So if the Higgs degrees of freedom are related by a symmetry, that means that the masses of the gauge bosons have to be related by a symmetry because the masses are caused by Higgs interactions. So hopefully that train of logic is clear or consistent. Okay. So we define the custodial symmetry with this parameter that we call rho. And rho is basically the ratio of the masses with some coefficients to make sure that we get there to 1. So this is the Weinberg angle. And if there was no U1 in the Standard Model, then we would expect this to go, the angle would be 0, but because there is, it basically tells you the mixing between the SU2 and the U1 couplings. But with the Standard Model and this residual symmetry, we expect this number rho to be equal to 1. Okay. And as you can tell, because we're just talking about anomalies with the W mass, we don't actually experimentally measure this thing to be that close to 1. So that tells us that for some reason, this global symmetry of the Higgs degrees of freedom isn't actually correct. So if we want to understand any sort of new physics contribution that could affect the W mass, what we can do is we can look at these operators that are in the UV that would correspond to violating this custodial symmetry. So things that basically break equal interactions between the Higgs degrees of freedom is what we want to see. So one example that we would see is with the Yukawas in the Standard Model. So this is strictly a Standard Model phenomenon, not new physics. But, you know, the W's talk to the up and down type quarks. And then if we include these kind of Standard Model effects, we find that we can have additional operators that look like this, and that will correspond to Wilson coefficients on dimension 6 operators of this form, right? And the fact that we're using the VEV here is again saying that the relevant scale of which we're measuring these things is that electroweak breaking scale. So it turns out when we do our measurements in the Standard Model, we find that this value rho is not equal to 1, but it's very close. So the deviation from 1 is measured to be less than 10 to the minus 3 experimentally. And so if we take this observable and we know that this kind of operator here, or this kind of diagram here, can be modeled by this operator of this form, then we can translate that to a bound. And it turns out that for V is 246 GeV, and we're assuming a coupling of order 1, then this corresponds to a mass scale of new physics showing up at around 3 TeV. So that is consistent with what we've seen so far, because we haven't been able to actually go up to 3 TeV in terms of collider physics yet. So the fact that there's not this huge violation occurring in this custodial symmetry, and the fact that the mass scale of new physics to show up to give us a bigger amount of violation has to happen at energies we haven't probed yet, is all consistent. So if the mass is well above the 3 TeV, then the contribution to this rho parameter would be even smaller, so it's not even experimentally observable. So yeah, this is all a consistent picture. Right? Another famous one in the Standard Model is baryon and lepton number conservation. So we've already talked about this a little bit with the masses of the neutrinos. We know that the anomaly-free symmetry is really baryon number minus lepton number, but I mean, effectively, baryon number is conserved and lepton number is conserved. And we've seen these things in a lot of ways. So we know that the baryon number is conserved, or at least approximately very, very well conserved, because of the fact that protons don't decay, right? Protons are the lightest baryon, and anytime you have something that's the lightest particle that has a non-zero quantum number in a conserved symmetry, if it's the lightest, that means there's nowhere it can go, right? Like it can't decay down to any other smaller particle. And if it's got a conserved number, it would need to decay into something that also has that number and something else. But the fact that it's already at the bottom means that having that quantum number be conserved means that it can't just disappear on its own. All right, so we see that baryon number is conserved by the fact that protons don't decay. And we see that lepton number is conserved very well by a lot of different kind of experimental measurements. So one of the biggest ones that we see is something like mu being converted to an electron and a photon or something like that. And this is a process that, again, we've measured extremely precisely, doesn't happen. So we've kind of experimentally confirmed that this big accidental symmetry of the Standard Model, this baryon and lepton number, is a pretty good symmetry up to very high energy scales. So we'll use the fact that protons don't decay to kind of set this limit on what kind of masses we might expect new physics could appear at if they were to contribute consistently with these symmetries. So given that we've measured the lifetime of the proton to be at least 10 to the 33 years, okay, the kind of operator that could generate proton decay is, again, a dimension 6 operator. So it's going to be suppressed by the mass scale squared. And then you can have operators like Q, 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 L. So clearly this is going to violate baryon lepton number because you can have something like a quark anti-quark producing a quark lepton. So 0 lepton numbers in the beginning, a lepton number in the end. And this would correspond to something like a proton decaying into a pion and then a positively charged lepton. Okay, and again, we don't think that this happens, and the measurement we've put on is 10 to the 33 years. And given that, for this kind of process, the mass scale of new physics would need to be above the gut scale, would need to be over 10 to the 15 GeV. So maybe there's physics above 10 to the 15 GeV that could be inducing a very, very, very small decay probability of a proton, but it would need to be so deep in the UV, basically, we couldn't have seen it yet at all. Okay, so any sort of indication of these accidental symmetries being violated in your IR tells you that there's some physics in the UV that's causing it, right? But in these cases where things are very well conserved, you have to be careful that any new physics model you introduce isn't generating an operator that would violate the accidental symmetries. Okay, so now that I've talked too much about indirect ways in which we can look for new physics, now I want to talk about some kind of direct searches that we can make. And again, because I'm a collider theorist, I'm going to do a very collider-centric description of it. But of course, there are other ways that you can do this with astronomy, cosmology, tabletop experiments, stuff like that. So colliders are really tantalizing because we can use this to go up to kind of the highest energy scales possible directly in a clean environment, right? So we call colliders is really the energy frontier experiments. So new physics can appear on shell in a lot of different observables. And then by measuring these observables, we can say more concretely whether or not we're seeing these new physics. So this is different from the EFT framework because we're not saying like, oh, there's something at much higher energies and we're just able to measure its little effects in the IR. The idea is that we are going up to that scale of new physics and directly producing it. So it's not like we have to worry about all the subtleties of like, oh, how is this going to, renormalize the mass of this one other particle? It's just we've produced it. It's there for us to see. So it's a much more straightforward and much more definitive way of, finding a new physics particle. So some of the biggest searches that people like to use, you've probably heard of an invariant mass or a bump hunt. And the idea is just that you're looking, if you have some distribution of the invariant mass of particles, seeing if there's some excess, which means that a particle is being produced at resonance, right? We can also look at collider events and see if there's a lot of energy that's just missing, that's being carried away by some weakly interacting particle that we don't see again. Or we can look at other kinematic distributions. We can look at the distributions of momentum of particles being scattered, or we can look at much more involved kinematic observables from a bunch of different other particles. Or we can look at things like event shapes, which tells you how particles radiate away from the center of the collision and things like that. So there's really a lot of different tools that people have to sort of dig out evidence of new physics, but always, again, it's in the framework of the standard model theory. So we're always trying to formulate what we would expect our predictions to be based off of the standard model, and then finding ways that we can very concretely see anomalous behavior. So let me talk about sort of the most canonical way that I think people want to see direct evidence of new physics at colliders, which is with an invariant mass bump hunt. So the idea is that maybe you have some sort of new physics process that looks like this. So you're producing on shell, maybe with partons. You're producing on shell some new particle. And the reason that we don't see it is probably because it's either very weakly coupled to standard model processes, so this coupling could be small, or it's so massive that it would decay away and doesn't exist at the low energies that we exist in our world, right? So you produce this new particle, it's heavy, it's unstable, and then it wants to decay into something, again, visible. So here are some kind of simple examples from actual results at experiments. So we have Atlas and LHCb, and they're giving results on models that look first like this one, and then I think this one is giving us models that look instead. Yeah, I think instead they're thinking about something that can mix with the Higgs. So maybe you're doing something like producing a Higgs boson. The Higgs boson can talk to any scalar, as we saw, because this is always going to be a singlet. So you can always make this kind of interaction. And then again, it has to go back to standard model final states. Okay, so if you recover the two particles here, you can sum up the four momenta. Oh, mu is a bad. Well, no, it's fine. So you can do the four momenta of the two particles, and then squaring it would give you the mass. So the square of the two four momenta is equal to the mass of the new particle squared. So in this plot, you can see they're showing what it might look like if you were to find a new particle at 3 TeV. So you see that, yeah, just taking the mass squared, you would expect that at about, oh, I didn't draw that line very well. As you would expect that at about 3 GeV, you would have this big peak sitting on top of your data. Okay, unfortunately, we haven't found any new beautiful peaks like that in our data. But if it were there, it would just sit right above all the other standard model stuff that you could be producing. Okay, and LHCb has done something similar. Again, you have some sort of prediction from the standard model, which is this central line. And then they're giving you 1 and 2 sigma deviations from your underlying standard model theory, which are the green and yellow lines. And then the black lines are just telling you what the data is. So as long as the data is kind of falling within that 2 sigma band of what we would expect, we're going to say that, there's not really strong evidence of some new particle being there. Usually we want to see at least a 3 sigma effect of signal above the data background, which is assuming the standard model, right? This tells us that there's some sort of hint, and then having a 5 sigma effect of having a bump that really shows up at a statistical significance of 5 sigma sitting on top of the data predicted by the standard model, that would tell us it's a discovery. So when we discovered the Higgs, we found with 5 sigma certainty this resonant mass sitting at 125 GeV. So of course we hope to repeat this process at, as we push to higher and higher energies, and this is kind of a nice idea because it's kind of reasonably model dependent, right? I gave you some examples of ways that we can have this new physics produced like this or like this, but really it's kind of model dependent, right? You're just looking at the final states of these things. So any new particle that's decaying into 2 final states, it might give you a resonance, and then we can hope to find it. So this is a very popular way to search for new physics. Okay. But although the results are pretty model independent, the searches themselves actually tend to be quite model dependent because experiments are very messy, difficult things, right? So with an experiment, you're not just getting back, oh, there was an electron here at this momentum with this energy, blah, blah, blah. There's so many more subtleties going on. So when you're doing an experiment, you really have to suspect, or you really have to narrow in on very specific aspects of the actual event that you're producing. So you can't just say, give me all the electrons. It has to be like, give me all the electrons that are produced at a certain angle with an energy of at least this, that have a momentum that look like this, and have to be produced with another muon or something like that. So introducing all of these extra parameters to make sure that you're confidently identifying your particle introduces all this kinds of model dependence. So there are ways that you can really get around a lot of these bounds just by changing sort of the structure of your model, and then you can evade experimental bounds. So, I kind of put this in the sense of, oh, it's kind of easy to get around bounds, but I again want to remind you of this Occam razors principle that you shouldn't just introduce new physics or arbitrarily complicated models for the sake of avoiding bounds. There should be some motivation to do it. So if you're doing this kind of analysis, make sure that there's a reason to consider a more non-trivial model than what's been previously experimented with. So that being said, with that caveat, let's think about a motivated way that we can evade experimental bounds. And basically what you're trying to do whenever you have a high data experiment like a collider is that you want to reduce the background number of events, which is, for our case, going to be standard model things, and you want to increase the relative number of signal events, which in our case would be from BSM. So if there's a way to make sure that you're cutting out with confidence standard model events without throwing away events that would be examples of beyond the standard model, then that's going to actually improve your sensitivity in your analysis. So the problem is if you just kind of arbitrarily do this, it's very easy to cut out not only background events, but also signal events. So that's not a super lucrative general strategy, is that you have to kind of think about some informed model building way to make sure that you're sensitive to new things and getting rid of standard model processes that you don't care about. So one example of, again, something that I've worked on is this idea of doing a mass bump hunt, but with a slightly more involved analysis strategy. So here, the diagram that you can consider to produce new physics, we're going to be kind of agnostic about exactly how it's produced, but we're going to say that you're producing some new particle, which we'll call, again, a Z prime, and then something else that can recoil into standard model final states. So all we really care about is this guy right here, and we'll say that it goes into muons. Okay, so there's a lot of stuff happening in the model, but this global feature of making some particle that's Z prime that's recoiling against some standard model particle is kind of the bulk of the model that we're trying to consider. Okay, and so when you do this, you're producing a Z prime that's got a PT greater than 0. All right, and so this is very different from the previous model that we considered, where you have something like this. So if you have two quarks incoming, right, the net PT of this process is going to be 0. So if you have two quarks colliding to produce one new thing, clearly that thing can't have any PT either, right? But if instead you're doing this process, where you're recoiling against something, is now you can have two quarks coming in and two things coming out. So because of the back-to-back scattering, you can actually be producing something with higher PT. So then, if you take this as your baseline model, you can improve the game of the S over square root of B by doing cuts on things that have low PT. So here's our standard model background events. And you can see that as we take higher and higher cuts of PT, we're reducing the number of standard model background events at each level. Okay, so as long as the number of signal events is also not reduced at each level, as long as it's roughly equal at every cut, then this number stays big and we're happy and we can actually do a more sensitive cut. But if, as we go down and cut more background events, we're also cutting out signal events like we would for this model, then it's a bad idea, right? Then you're not improving your sensitivity, you're just throwing away data, and that's not super useful. So when I say that, sometimes it's easy to kind of get around bounds, you have to do it in a motivated way. Otherwise, there's no point. You can't just like create stuff that like, oh, assuming that this could work, let's go for it. It's like, okay, given that there exists a class of models in which this is a viable strategy, that's how we're going to do it instead. All right. So I saw there was a quick question. Oh, what kind of books? I will give books at the end. How about as further reading? Because again, this is such a huge topic. Okay. So of course, depending on all that I said, there's ways to miss new physics signatures, and this is why we need a lot of physicists thinking about how we can develop interesting new physics searches at things like the LHC and beyond. Okay, and then a super quick note about being consistent with cosmological data, because I gave you a very collider-heavy introduction there. There's a lot of different measurements in cosmology that they make. So the number of light degrees of freedom and effective is one, the Lyman alpha forest, just the relic abundances of things as the history of the universe, the abundance of dark matter, the 21 centimeter signals. All of these things are also ways that you have to be consistent with measurements. But again, because they happened in a much messier environment, there's a lot easier ways to sort of get around evading these constraints, as long as it happens early enough in time that the effects are washed out. So there are certainly collider constraints or cosmological constraints that are different than collider constraints. But in general, it's kind of easier to find ways to sort of, get around these things too. Okay. And really, there's tons of other experiments that we can use in general. I'm giving you a super collider physics centric perspective. But yeah, take that with a grain of salt. So now I want to finish by talking about what are some common BSM theories in modern research that people have spent a lot of time thinking about. Okay, so given I led in with so much about dark matter and WIMPs, or dark matter, I want to talk about the primary way that people think about dark matter model building, which is with the WIMP paradigm. So again, to kind of go back to the motivation of dark matter is from different measurements we've made. We know that at the time of the CMB, dark matter must be non-relativistic. Because of the fraction of primordial helium, we know that it has to be non-baryonic. And because of the things like the bullet cluster, we know that it has to be weakly interacting with the standard model and itself. And the fact that this class of matter has persisted to modern day means that these particles have to be cosmologically long-lived, which means that they don't decay on the timescale of the length of the universe. Otherwise, we wouldn't see any sort of abundance. So given all of these constraints, there is no standard model candidate that makes sense. You might say, okay, maybe neutrinos, which is sort of the first guess, but neutrinos are way too hot and non-relative, or way too relativistic to have given rise to the large scale structures that we see. So there's no standard model candidate that really makes sense and can address all of these aspects of dark matter at once. So because this is such a persistent problem, of course, people have done a ton of model building attempts to try to solve it. And that's this sort of huge span of like 10 to the 30 something orders of magnitude of solutions. So the very light solutions, we have these bosonic fields that effectively look like classical fields because their wavelengths are so long and they're so light. You have in the other regime, basically primordial black holes. Black holes gravitate a lot. The whole thing about dark matter is that we see gravity. So perhaps black holes from the early universe could be causing it. But really the thing that I think is most compelling and most motivated is this section here called the WIMP, which is dark matter candidates that are sitting between sort of 10 GeV and 100 TeV masses. Well, okay. So just to give you an idea of what the WIMP is, the idea is that if we try to think about what's going on in the early universe, we can think about this annihilation process that goes back and forth between standard model particles and dark matter particles, okay? And if this process is happening fast enough, the standard model and the dark matter should share a same temperature, right? This is what we call thermal equilibrium. This is when the interaction rate is sufficiently fast on both sides that they can equilibrate and have the same temperature, okay? So when particles fall in this thermal distribution, they follow a Maxwell-Boltzmann equation, right? And that tells you basically how many particles you expect to see at a certain temperature, right? So when the temperature falls below the mass of the particle, the probability of finding a particle at a certain energy is going to fall off exponentially. Exponentially with this distribution. Okay, so basically, as long as these things are in thermal equilibrium, once the temperature is below the mass, because you can no longer produce them in these kinds of scattering processes, we expect the population of them to be very low, and they're suppressed by this exponential factor. However, because the universe is expanding, we'll say that the rate of interaction, which we'll say is this gamma, as long as this rate of interaction is greater than the rate at which the universe is expanding, this process can proceed, right? Like we can have these things happening. But as the universe expands, an already small population of dark matter is going to get even more dilute, which means that the cross section of interacting is going to go down even further. So at some point, when the rate of interaction dips below the rate of expansion of the universe, this process stops. Okay, and this is called freeze out. Because basically, as soon as this happens, the amount of dark matter in the universe is kind of frozen because there's just not enough dark matter to annihilate and go back into standard model. And the rate of this happening is so infrequent that no more dark matter is being produced. So we call this freeze out, as in the relic abundance of dark matter is frozen. So if you've seen this plot where you have basically, I think it's like the entropy normalized density as a function of the mass over temperature. If it followed a Boltzmann distribution, we would expect dark matter to fall off like this. But the fact that this freeze out process happens is that it falls off, follows the Boltzmann distribution, and at some point it just stops. And then this is the relic abundance that we see today. Okay, so what the WIMP miracle is if this process occurs through an electroweak boson, so the W, let's say, or a Z or something like that, if this is electroweak mediated, then we expect, given the relic density that's abundant today, then the mass of the dark matter candidate would have to be sort of around the electroweak scale. So this is really exciting because it's predicted by supersymmetry, which we'll talk about very briefly on the next slide. But basically, the idea is that if standard model and dark matter interact with electroweak processes, then dark matter itself should sit at the energy scale of electroweak processes. And so this is what we call the weakly interacting massive particles, or the WIMP miracle, that basically electroweak sector could be dark matter. So not a particle that we already know, but a particle that behaves in ways that we understand with the electroweak sector. Okay. So this is usually what a lot of attention goes to. I think nowadays people think a lot more about PBHs, primordial black holes, or this idea of the QCD axion as well. Okay, given that I just talked about SUSY, I think I need to actually explain what SUSY is. And SUSY is one of the most rich research fields of particle theory, so I couldn't begin to cover all of it, but let me just give you a very brief motivation. We already talked about how the mass of a scalar particle is going to be quadratically sensitive to loop factors. All right, so the fact that we don't have the mass of the Higgs sitting at like the Planck scale, the only cutoff that we know, tells us that, okay, maybe there could be some new physics closer than the Planck scale. However, if instead these contributions could cancel each other, then we don't have to worry about this quadratic divergence, right? Then if we have a small number for the mass and the higher order corrections cancel each other, then everything's fine and we don't have this hierarchy problem. So the idea is that we can get sort of this loop, which is the Higgs in a loop and fermions in the loop, to cancel each other if we introduce some sort of symmetry that relates fermions to bosons. So we want to introduce some operator that takes a fermion to a boson and a boson to a fermion. And with this, we can resolve the hierarchy problem. So this additional operator, and the fact that we can relate bosons and fermions, is the idea of supersymmetry. So it's supersymmetry, as in it's a greater symmetry of the standard model, right? And the idea is that we organize all the fermions. They have supersymmetric boson counterparts. And same thing, the bosons have supersymmetric fermion counterparts. So that's what this table is summarizing here. So in the standard model, we have these spin half fermions, the left and right quarks. And then with SUSY, we have additionally these spin zero bosonic degrees of freedom that have the same quantum numbers under the gauge groups of the standard model, and should therefore have some mass as well for these things. So the number of degrees of freedom for the fermionic sector has to match the number of degrees of freedom in the bosonic sector, and then all of these things together form what we call a supermultiplet. And if this were true, then the hierarchy problem would be completely solved, no problems. But of course, it's not quite so simple. So if we had these supermultiplets where all these particles had the same interactions and the same mass, surely we would have seen them by now is the problem, right? We would have turned on the LHC and all of these superparticles would have fallen out and we would have seen them instantly. But unfortunately, we didn't. So that means that supersymmetry is not a good symmetry in the IR. It has to be spontaneously broken. And that introduces again the problem of, okay, well, at what energy scale does SUSY break? So there are relative ways of creating this sort of like elegant to very inelegant ways that we can break supersymmetry in a motivated way. But really it doesn't have quite the same mathematical elegance as the original theory did. However, it's very useful for model building, and again, depending on how convoluted you want your scale of SUSY breaking to be, there are ways that SUSY can still survive. But yeah, this idea that the fermions and bosons were mathematically related by some operator was a really promising insight that unfortunately didn't quite work out. Okay, so then going back to this idea of the WIMP paradigm, is that you can actually build dark matter particles out of the super pairs of the gauge bosons and the Higgs bosons. So the most basic WIMP scenario is just taking the neutralino, which is built out of the neutral components of the supersymmetric gauge bosons, and making that dark matter. And that would be consistent with the WIMP picture. But again, since SUSY can't be the most minimal form, we can't have that model for dark matter anyways. So yeah, it's not quite as tantalizing as it once was to have this be a solution. Oh, okay, here's my plot of freeze out. That's great. Yeah, so here we go. Here's our freeze out in case you wanted to see an actual picture. But yeah, this falling off corresponds to the Maxwell-Boltzmann distribution. And then the freeze out here corresponds to the rate of interaction between standard model and dark matter, dipping below the rate of Hubble expansion. Okay. Sorry, that got put out of place. Okay, so coming back to this story now that we've discussed SUSY a little bit, again, these WIMP models have to do with having these higher multiplets of SUSY. And at the bottom of the multiplet, you have this sort of lattice state that again is protected by a symmetry. So that would mean that it doesn't decay, which is another aspect of a dark matter model. But of course, since a lot of these things have been studied or ruled out or are no longer theoretically consistent, you have to sort of get to these arbitrarily complicated multiplets, which again become kind of more and more unmotivated, but evade bounds. So you got to kind of do this trade-off between, do you want something very simple or do you want something that is a well-calculable structure and that you can study? And the answer is probably doing some of both. So I've kind of presented this a lot in terms of collider physics, but you can also do things like, this is direct detection is directly producing it, but you can also have indirect detection, which is where you have these big experiments that instead of scattering dark matter, and standard model like this, instead what you're doing is dark matter is recoiling against standard model particles like this. So there are a lot of ways people study for dark matter, and unfortunately we don't have a single particle description that's consistent yet. Okay, I see that I'm out of time, so let me just say some very quick things about first the seesaw mechanism, and then I'll finish with axions, and I guess that's where I'll wrap up. So sorry for going a little bit over time, but thanks for bearing with me. So coming back to the seesaw mechanism, again, we have this dimension 5 operator, which is our Weinberg operator, which tells us that we can have these neutrino masses. So once the Higgs gets above, then with this operator, you are generating the term that looks like the standard Majorana mass operator for your particles. Okay. So we found from experiments, either with this Captrine experiment, which gives you an absolute scale of the neutrino masses, or with neutrino oscillations, that the difference in neutrino masses has to be on the order of at most 10 to the minus 3 electron volts, but at least around 10 to the minus 5 electron volts. So the masses are split, but they're split by very small numbers. Okay, and the overall mass we know has to be below even 1 electron volt, which is much less than all of the other particles that we've seen in the standard model. Okay, so this could be seen as a big triumph of the standard model because we know that this operator violates lepton number, and lepton number is a good symmetry of a renormalizable theory. So the fact that this accidental symmetry is preserved means that, yeah, okay, maybe there isn't something new in the UV that's generating this. However, we can also think of models that are generating it very high in the UV, and therefore are not only consistent with this mostly preserving lepton number in the standard model, but also could generate these very, very small masses. So the idea is that you introduce one more neutrino, which usually they call an R. There are various kinds of models, which are type 1, type 2, and type 3. But basically, for the interest of time, let me just describe very quickly what type 1 is. So the idea is that this is some particle that's going to be basically not a singlet, but yeah. Okay, so in type 1, we'll say it's a singlet of everything in the standard model. And then you can have interactions with standard model particles of the type like this. So a Higgs, your left-handed particles in the standard model, and your right-handed new particle. So from there, basically, if you go and you build a mass matrix of these particles, you find that these things are mixing, and there's some off-diagonal components to what this mass matrix would be. Okay, so if you diagonalize the mass matrix generated by this additional term, Yukawa term in your Lagrangian, you find that the mass of the neutrino is going to look like V as in the Higgs vev squared over this new mass scale, whereas the mass of this new particle is going to stay roughly around the very high mass scale. So it's called the seesaw because if you push up the mass scale of your new particle, you're pushing down the mass scale of the neutrino. So it's this very smart way of sort of making sure that you're going to not be generating too big of masses, especially if you're going to higher energy scales. So just to give you an idea of what that would look like in terms of your diagrams, right? If you have a normal Dirac mass, you have your left, your right, and then a Higgs insertion to give you the mass. If you consider your dimension 5 operator, which is this guy, then what you're seeing in diagram level would be like 2 insertions of your left-handed field. But then if you go to higher energies and you can see what's actually happening at this effective operator, is you see there's really this new heavy particle showing up in your interactions. Okay, so there's a bunch of variations on the seesaw mechanism. Here are a bunch of open questions still about neutrinos. And yeah, clearly, clearly neutrinos are a very active part of BSM physics, partially because they're so weakly interacting, they can evade a lot of bounds, and there's a lot of interesting questions still surrounding their nature and their masses and things like that. So one of the biggest questions is really, I have to say, are neutrinos Dirac or Majorana fermions? As in, do they get their mass through a Dirac mechanism, meaning a left and a right-handed field, or do they do it with Majorana, which is the same field as in this model? So the way that we can definitively prove this is by doing experiments with double beta neutrinoless decay, which involves this process of neutrons decaying. And then if a neutrino is Majorana mass, this process can happen without neutrinos in the final state. Okay, so if we observe this process to happen, this neutrinoless double beta decay, then we know that they are in fact Majorana fermions. But if this process is not observed, then they have to be Dirac. And this is something that's really ongoing and very important for new physics. Okay, and then the final model, I know I'm super out of time. I'm so sorry. Let me just get to this really quick, is this idea of axions. And I would say axions has kind of taken over in terms of BSM model building, in the thing that people are most active in and trying to figure out how they can build on axion models, how they can study axions in new ways, and this kind of thing. So basically axions are the solution to why is the CP violation in the strong sector so small. Okay, and so we can see this by basically knowing that if we write down all the terms that are allowed in Lagrangian, we should be able to write down this additional term in the strong sector, which couples the field strengths, but not in the normal way, instead with this dual. So what the dual means is that it's contracted with the epsilon tensor, which means that this is going to be inherently CP violating, right? Because the epsilon tensor is a CP violating tensor. Okay, so we should expect that this term would show up in the standard model. However, we don't see it, right? We don't see any sort of CP violation with gluons, right? So this is saying that we have this number that we should expect to be finite, that's really close to zero. And we have to find some way to make sure that it makes sense that this number should be zero. So there should be some global like some overall symmetry that would predict this number to be so small, which is the same kind of thing that we're doing with Susie, right? We're trying to find some symmetry that explains why a number is so anomalously small. So the idea that people include usually is considering this additional pseudoscalar called an axion. And then an axion, because it is also a pseudoscalar in CP odd, can couple to this term as well, so that this term is going to be allowed in the standard model. Okay, so clearly this is a dimension 5 operator, so it has to have some UV completions. The most common UV completions are either the K, S, D, Z, or the D, F, S, Z. I wish I could remember all of the last names. They're all very Russian, and unfortunately I don't remember them all. But these are the kind of two most common UV completions that will give you this operator in the IR. And so the idea is that if you include this into your Lagrangian, now the total Lagrangian is going to include this axion field, plus or minus, it doesn't matter, times this operator, and also some coefficients, right? So if you want to give the axion a vev, or if you're minimizing your theory, you'll find that the axion will take a vev that is equal to this dimensionful or this dimensionful parameter FA times whatever value this theta would be, such that this term goes to zero, right? Because a lot of energy is carried in this term in the ground state. So the universe wants to minimize this term. So basically how you might hear about it is the axion is going to be the Goldstone boson of some new U1 symmetry called the Pesce-Quinn symmetry that's secretly anomalous, which is why this is the axion can have mass and there's no problems. And then basically it dynamically sets this theta to zero. Okay. So what's also really wonderful about axions is that they can exist not only as a solution for CP violation, but also for dark matter. So a lot of these searches here you can see from CMB and X-rays and kind of in here is that people are looking for axions as a solution to dark matter in addition to being the solution to CP violating. But people really secretly mean, you know, anytime you have this sort of pseudoscalar. So you might also see axions described as ALPs or axion-like particles. Okay, but this is something super well searched for. You'll see that a lot of this space that can explain the CP violation here is still pretty unruled out. There's still a lot of openness. So a lot of the name of the game in designing axion experiments is finding out ways that we can actually still be sensitive to this regime where axions are not only some new particle that could be dark matter, but also resolving that CP violation as well. So a lot of these experiments happen in these resonant chambers where the idea is you have an axion incoming, and then because of this term that you have near Lagrangian, you know, axions can couple to two photons. So you have some sort of classical field. And then you can convert the axion into a photon, and then the photon can be resonantly detected in some kind of experiment like this. So these experiments are very effective, but usually function in a very small mass range, which is why it's so hard to get all of that parameter space. Okay. So yeah, my last statement was just that, okay, you can also just do random extensions of the standard model just because, you know, we don't have a complete picture of the universe. So there might just be new stuff. So it's important to kind of keep your mind open to being able to look agnostically for new physics models. But building a research program strictly around, well, what if this could exist, is probably not the most lucrative way to do it. Okay, so given that I'm so over time, let me just wrap up right now. Basically, there are a lot of other important models for BSM. BSM is a huge field. I had an impossible task trying to summarize it in 2 hours, but I hope that you at least understand how we do some BSM, what kind of models there are, how we can look for it, what experiments are relevant, and things like that. So there are tons of other models that are important and super relevant that I didn't have time to mention. And I hope you can walk away with this lecture knowing that, there's a lot of active work being done still in BSM research. So thanks so much.